command in Stata called expose, which the X means cross or transpose. But what the transpose data will do is it's different than the reshape. What I'm going to talk about is the reshape. Do you guys know if there's like a remote clicker, or does does everybody walk back and forth?
No.
There's a remote clicker. It might be in that closet. I can ask Elliot.
Yeah. Okay. All right. So here's an example of data that are stored in what we refer to as the wide format. So you might think of this as a polling data measured across the 2000 election and in the 2004 election. So here I have repeated measures data. I've measured the Democrats' vote in 2000, and I've measured the Democrats' vote in 2004, and the same thing for the Republicans. So this is what we refer to as a wide format. The thing that you'll notice here is that the variable names have prefixes on them, and they have suffixes on them, right? So if we know that, if we understand the structure of the data, we can take advantage of that knowledge that here I have a Dem or a Rep. This is the prefix that this tells me this is the Democratic 2000, this is the Democratic 2004. We can take advantage of that, and when we want to convert things from wide to long and then long to wide. Okay? You with me so far? This is the same data when we reshaped it into the long format. So here what we see is that we have transposed it such that each observation corresponds to one and only one measurement. So the top line here, instead of saying, Ohio Dem 00, and that value being 2186, now we have this row contains only those data for Ohio Democrats 2000, 2186, right? So when I have the data this way, I can fit mixed models. So to tie this back in with regression, for example, the reason that we talk about long versus wide is if I'm in Ohio, do you think the voting patterns in Ohio from 2000 should be correlated or related to the voting patterns for the Democrats in Ohio in 2004? Probably. So are these observations independent of each other? So we have violated that distributional assumption of that error, right? So when we have data like that, where we violate that independence assumption, we ought to fit mixed models to take into account that lack of independence between those observations, and this is how we would need to set the data up to do that when we run the XT commands in Stata. Okay? So this is how we would do it. Grab a drink here. So when we want to go from wide to long, we're going to execute the reshape command. And then what we're going to do is we have to tell Stata what direction to change the shape. So this after reshape, it's either going to read long or wide. So when we go from wide to long, we have to think we're going from wide to long. And then you'll notice here I have this BP, but I don't have these suffixes, right? So I have BP variables there. And here I have an I patient. So what's going to happen, if you can think of it this way, so I would have data that would look like this. I would have patient BP underscore before BP underscore say after, right? This is a little bit different than the voting data. Because in the voting data we had the years, which was numerical, but in this data we have a string. Make sense? Okay. So we can do this transposing whether or not we have the data. I could have written the same data set and I could have named the variables this way. Right? I could have named it BP0 like a baseline, and then BP1 like a post-treatment measurement. So here the suffix is numeric. Here the suffix is alphanumeric. You with me? So Stata can handle both alphanumeric or all numeric suffixes. But if you're dealing with an alphanumeric suffix, you have to tell Stata that the suffix to the variable that you're dealing with is a string. A string means something that's alphanumeric. Okay? So what's going to happen here is that we say reshape long, because we're in a wide format now, the BP underscore variables. So if you see all of the variables have the form BP underscore and then the suffix, right? And then we have to say, okay, what are we going to pivot on? What are we going to pivot on? We're going to pivot on the patient variable, right? So we're going to pivot on this patient variable. So it's going to create a data set that's going to be patient, and then it'll have a variable called when. Okay?
What is the J?
The J, it's going to create a new variable. So instead of having before and after, it's going to create a new variable called when.
And that's going to be whatever the suffix is.
Yeah, so when will contain before, the strings before and after. And then it'll have another variable called BP underscore. And then the BP underscore will have the numeric value that corresponds to this patient for this particular temporal measurement.
Would you just not have a string in there if you were using BP0 and BP1?
Yeah, then you wouldn't need the string. It's smart enough to know. The other thing that's going to happen is when you execute this command, it's going to sort the data for you. So when the data are numeric, the 0 comes before the 1. So when you get your final data set, it'll be like patient 1 before is going to be a 0. Patient 1 comes after, and then you'll have, I don't know, 150, and let's say that the drug worked and it brought it down to 120, right? So it'll look like this. If the data are going to have the strings, instead of 0, 1, it would say after, and then before. Notice A comes before B, so when it sorts it, A is going to bubble to the top.
So you can only do this when the two variables that you're using start with the same?
Yes, same prefix. Yeah. Okay. So this is an important point to make because a lot of times we're interested in looking at the data sequentially. We want to look at the first measurement and see how the second measurement and then the third, fourth, and so on. And if we do things alphanumerically, we have to acknowledge the alphanumeric sorting of the data when we examine.
Well, Democrat and Republican don't start with the same. We should have said that only works because BP underscore.
Yeah, in this case, a BP. What I could do in
So
the
if it
other,
was the Democrat Republican, what would you have written there?
I would have written reshape long dem rep.
Oh, so then it will take out the.
Yeah.
So then it will make the dem and then O.
Yeah.
O1.
And then that one would have been I, just to like go through that one for another example, that would have been comma I,
Yeah, I state, yeah.
And then J.
Would be time or year. I'd probably call it year. And then it would take on the value of 0 and 4.
If you're would you need a string? Oh, sorry.
Oh, go ahead.
Would you need string though? Because
No.
they're numbers now.
No, because they're numbers. I wouldn't need the string because it's numeric. That's a good question.
How did that one end up split into party? Like, would you give the example on the next one, the long data? The top things are swing state, party, year, vote.
Well, I could have said the when could be party. Sometimes you have to do a double. You have to reshape it twice. Okay, your question?
If you're working with a large data set and you're only using certain variables, do you need to extract your variables of interest first and make a smaller table? Like if you're pivoting, will it just pivot everything?
It'll pivot it. Well, in this case, what'll happen is it'll throw everything that's not into the thing. It'll pivot. It'll go into this pivot, into the I
Okay.
statement. But if you're only interested in a certain subset of variables from a much larger data set, that's a separate question. And my strategy for that would be when you use the file, so there's the use variable name command.
Right.
What I would do in that case, see, these are all great questions that you sort of can't anticipate when you're coming up with this very general curriculum. So I would actually execute the command that would look like this, var1, var2, using file name. I don't know if you can read this, but this says use variable, 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 using the file name. And then that way, you won't have to keep or drop anything, because you've essentially done the keeping and the dropping in your use statement. And the extent to which you can do that when dealing with data, always do that. Because, and especially in Stata, and I don't understand why Stata does this, but the smaller the number of variables there are in memory, the faster everything executes. So even if I'm interested in doing a correlation between two variables, if I had 1,000 variables in my data set, that bivariate correlation will execute orders of magnitude faster if I only have those two variables in my data set, as opposed to having all of them in the data set. So when I deal with very large data sets, and I have to do I want to look at associations between one variable and a whole bunch of other things, depending on the size of the data set, I'll do some experimentation. And sometimes my solution is to constantly only read the two variables at a time that I need, because it's faster. And I don't know why Stata does that. And again, for small data sets that like we would use in class, you're not going to see any difference. But for real data sets, like again, I'm only working with Kristen in this case, so if I keep referring to her, that's why. She has very large data sets. And in that case, it's probably more efficient to keep reading the very small variables from the data set at a time, as opposed to keeping everything in memory and having the disk thrash all the time, right? And that's not in any user documentation. Instead, you just learn that from working with it for a long time. But did that kind of address your question? It's sort of there, right? Okay, all right, so in this case, notice, this is what we're talking about here. All right, so when we go from, before we were going from wide to long, the syntax is essentially the same, right? So I need a reshape, and now instead of going from wide to long, now I'm going from long back to wide. It's what's the direction I want to do the transposition. What are the variables that I want to transpose? And again, where's my pivot? What's my pivot? And then what's going to be the other variable, what we refer to as the time varying variable. Right? So when tells me this is the name of this tells me the differences between the times. That's what this is. we're going to cancel class because you didn't show up.
Yeah.
Okay, all right. Now, I was talking about the expose command, and this is different. Right? I keep talking about transposing. Reshape really isn't a transpose, it's more of a pivot. Whereas transpose is a true transpose in a mathematical sense. So remember from algebra, you could transpose a matrix, rows become columns, columns becomes rows. You can do that in Stata. And this is what we call a destructive command. It's a destructive command in the sense that you can't go backwards. So if I reshape from wide to long, using all of that syntax, I can very easily go back from long to wide if I go reshape long. If I go from wide to long, the data are now long. And if I want to put it back in its wide format, I only have to do reshape wide. I don't have to have all that other stuff. Right? So I can go back and forth with that pivot. But for the expose, once you transpose the data in a true transpose, like in a mathematical sense, you can't go back unless you read the data from the disk again. Right? So there's a difference between reshape, which is really a pivot, and transpose. Okay? I've been using Stata for 15 years, 17 years, something like that, and I think I've used this expose command twice when I was doing simulations. And I like crazy, weird kind of mathematical simulations. And but I just wanted to make a distinction between the reshape, which is a pivot, as opposed to a transpose.
So it won't save it that way unless you actually save it.
Yeah, right. Yeah, but notice here, there's the clear command or the clear clause. If you just do expose, it'll refuse to do it. Stata will say, no, I'm not going to do it. Because it's destructive in the sense that you can't go back with the data that's in memory. So to do this transpose, you actually have to say, no, I really want to do it, by giving it the clear parameter here. That's one of the things I do like about Stata a lot, is that we talked about this before, is that you have to intentionally shoot yourself in the foot. So it's really good about that.
Is there any reason you use this over reshape?
I never use this. Like I said, I use Stata almost daily, professionally, and I think I've used this twice, but in a very specific case where I was doing a massive simulation. Well, I can't actually think of a case. A lot of times you'll get data in Excel. So let me get on my soapbox here for a minute. If you're going to do research, do not use Excel as your database. Excel, you can put anything in the cells and it'll take it. So sometimes people will set up their database in Excel where it might make more logical sense to make the columns be the variable names, and they'll do it ass backwards. And a really quick way of fixing that would be to use this expose command. But other than that, I mean, for an everyday, I can't think of any way that I would use that. But with the way that people use Excel, I can imagine quick fixing that. Okay, so that's reshaping, which is really pivoting, right? Okay. Okay, so I know in Andy's class you've been talking about propensity score analysis and things like that. So in this case of propensity score analysis, there's things that we can do quickly, right? So in epidemiology, how much you guys know about epidemiology? Nothing. So do you know the concept of a case versus a control in a case control study? Okay, so let's go with that simple design. So in a case control study, we're going to go case. So a case is the idea of somebody who came down with the condition of interest. A control is somebody who did not come down with the condition of interest. And then we're going to look at exposure to something and then non-exposure to the particular risk factor. Okay, make sense? So this is a typical 2x2 case control exposure, unexposed kind of thing that you would see in epidemiology. And you want to look at the association between exposure to some caustic thing and the probability or the likelihood or the relative likelihood of coming down with some heinous disease as a result of being exposed to the caustic thing, right? So a lot of times in the data sets, it's particularly in journal articles, you'll get what we call, you'll get the tables. 19960. Okay, so that is our case control table, right? So what we can do here is that we can look at, without actually having all of the observations, you can execute what are called immediate commands within Stata. So if we have all of the information we need to compute an odds ratio, in this case the counts, we actually don't need all of the observations. We can use these immediate commands. So these commands that end with I in Stata are immediate commands. So what this will do, these immediate commands, was they'll do things like logistic regression without having to capture all, 25,000 observations in your data. You can just have the counts and know the classifications of those counts to come up with the odds ratios, including confidence intervals and p-values and things like that, right? Which is actually quite helpful. So, yes.
So if you had a database with all, like, say 25,000 entries, then you also had those numbers, and you could calculate the odds ratio either way, right?
Yep.
I mean, is there an advantage to doing it?
Let's say you don't have all the data.
Okay, so then just do that.
It'd just be this. Wait, does anybody have Stata on their computer?
Yeah.
Did it work? Pretty cool, huh? So you did this and you did this, right?
Yeah.
Right, so this command uses all of the data, so you need the data to compute this command. This command, you don't have to have anything, you just plug it right in and it executes and you get the same results. Because essentially what this command is going to do is it's going to take your data, count them up, classify them as you have done that, and do what this is going to do. Right? Okay. Fair enough. So you got an odds ratio, right?
Sorry.
That's okay.
There's a risk ratio different than risk ratio?
Yeah, risk ratios and all that stuff. Right. Okay.
Are you going to talk about what those commands are?
Not specifically.
Okay.
You can look these up.
Okay.
What is the CS?
Pardon?
What is the CS does?
You tell me. Type search. You guys know how to use the help in Stata? So search space CS. What does it say?
So it has an immediate command that I think I should have done help.
Yeah. Okay.
It says cohort study.
Oh, tables. Yeah, it just says tables for epidemiologists.
So with these kinds of studies, you can get risk ratios, risk differences, relative risk, odds ratios, those sorts of things. Okay. All right.
So is that basically the work with aggregate data?
Yeah.
Is that what you were?
Yeah. So this is the aggregate data.
Okay.
Right. So we have the concept of case control studies and other kinds of epidemiological studies where the difference between the study type is how you've selected your participants or how you've identified your participants. But it's the same concept here. Okay. Right. More of the same. So here you could look at incidence rates. So we have case controls, case studies, and incident rates, right? So that's CS, CC, IR. There's all sorts of other things that are in there. Okay. So you can use it like a calculator using the immediate commands. Or you can use the full-blown commands. But the idea with respect to epidemiology questions is what kind of study is it, right? So you need to think about what those things are. Right? That's not the purpose of what we're talking about there. I just wanted to expose you to the concept that it has these things built into it, case controls, those sorts of things, okay? The other thing that Stata has built into it is it's got a sample size and power calculator built right into it, which is kind of neat. Many times studies fail. They fail in the sense that you don't find a statistically significant association, not because there isn't an association, but because the sample size isn't large enough to detect the association, right? So in that sense, people haven't planned their study accordingly, right? So remember the chaos table that we came up with before, and then we said, we came up with the concept of true state of affairs. And we said, the null is true or the null is false, and then we judge, so we either fail to reject or we reject. Remember we did all that? And then we had alphas and we had betas and 1 minus alphas and 1 minus betas. Remember all that stuff? Okay. Well, when you plan your study, when you get to design your study from scratch, if you're going to be doing data collection on your own, new data collection, guess what? You, the investigator, get to decide on your level of alpha and your level of beta. You get to choose that. The other thing that you get to choose, which is a very important thing to do, is that you get to decide what a clinically meaningful difference is. So there's a big difference between clinical meaningfulness and statistically significant, right? So say I came up with an intervention that lowered that blood pressure from an average of 150 to 149. And I conducted a study, and I got a very small p-value. What would you say? You'd be like, whoop-de-flip-and do, right? And then people would go, oh, but the p-value is really small. That must mean that it's really important. And of course, you would say, what? Whoop-de-flip-and do. That would be the appropriate scientific response rebuttal to that, right? So here you get to talk about what are the meaningful differences. What is a meaningful difference, right? And you do that when you design your studies, right? So those are the things that you need to know, or the things that you need to guess at when you're designing your study. Your choice of alpha, your choice of beta. You need to know the expected outcome for one treatment, the expected outcome from another treatment, and the variances associated with those outcomes. Right? And once you have all that information, you can figure out, well, how many people would I need to give myself some amount of power to reject the null hypothesis at some level of alpha under the assumption of this big a difference between the two groups with this much variability in the outcome. So you guys get to decide that, which is kind of empowering, I think, as opposed to going out doing a study and hoping to God that you get something interesting and you haven't wasted everybody's time. I actually think this is a far more disciplined way to go. And you're not unnecessarily exposing people to risk If you underpower the study, that is, you have no shot in hell of rejecting the null hypothesis because you don't have enough people to find it, so you've exposed people to something that doesn't work. Or conversely, if I have something that doesn't work as well, maybe you want to do a placebo-controlled study, you've unnecessarily undertreated a whole bunch of people. Right? So there's ethical considerations that go into the design of studies. And conversely, let's say that you not only does your medication not work, but it has a deleterious effect. So we have to think about minimizing the risk of that, okay? Okay. All right, so let's talk about this for a second. All right, so we've been talking about this sort of stuff. Usually what happens is by convention and religion, generally we set alpha to be 0.05. But there's no reason we need to set that to be 0.05. The other thing that you'll need to choose is beta. So if you remember what beta is a type 2 error. Beta is the probability of failing to reject the null hypothesis that is false. So in that case, it's a false negative. There was a difference, but you didn't see it. And by convention, we usually set power, so 1 minus beta is what we refer to as power. We generally set that to be about 0.8. Right? But if it's very important to you to find that effect, to observe that effect, you might go as high as 0.9. Right? So by increasing the power, you're decreasing the probability of a beta error. Right? Because these two things are going to be linked. Make sense? So there's an immediate command in Stata called samp_psi. Samp_psi. Okay. So what this will tell me, by computing it this way, it's going to give me power. So samp_psi, let's look at it this way. This is the command we would use to look at the power of comparing two means. So if I want to compare two means, what kind of test would I be doing? A t-test, an independent samples t-test. So if this is the sample size in one group, and this is the sample size, or the mean in one group and the mean in the other group, and this is the standard deviation for each of those groups respectively, and these are the sample sizes for each of those groups, I have everything that I need to estimate or compute power. Now there's also a thing that we could do, for example, if I know I wanted to have some fixed ratio between my treatment and my control group. Let's say for every control patient, I wanted 2 treated patients, right? I can set up a ratio here. So in this case, there will always be twice as many treatments to my controls. So you can play those games as well to figure out what's going on. Now the one thing that, I don't know if you've learned this or you talked about this in introductory statistics class, but the best way to maximize power in a randomized clinical trial is to have equal sample sizes. So think about it. Okay. Oops. Here we go. Excuse me. The other thing you can do is you can also compare proportions. So instead of just means, you can look at the difference between proportions. So you can do that too. So under Stata, under statistics, under the menu, if you have Stata running on your computer, under statistics, it'll say, I think it's the first entry. You mind if I look over your shoulder?
Yeah, the summary is here.
Yeah, under that, you'll see it says classical test of hypotheses. There's lots and lots of designs that you can fit with Stata. Okay?
The reason again that you would use the R here?
It's the ratio of one size to the other. Okay.
So that's just that's as compared to whatever number you're gonna get first. So if you said N1 35, R2 is gonna just assume 70.
Yes.
And the P in that last one was, P.8.
Oh, you're going to compare. You're going to assume that the outcome is 0.8 because you're dealing with proportions.
Can we go back for a second to the one where you had 130, 150?
The means, right?
The means, yeah. So what if you were like, if that's, let's say that's blood pressure,
Mm-hmm.
if you wanted to be like, I want to be able to detect a 10-point or a 15, instead of saying it like that, you said I want to be able to detect a 15-point difference in blood pressure.
Okay, now
Because you said that the 1 point, like 1 point is silly.
good question. So the one thing that, let's talk about that. Let's design a trial. Okay, let's design a trial. And let's talk about the information that we're going to need. Okay? So let's make these decisions. So the things we're going to need are alpha. Let's decide on that.
0.5.
Okay, 0.5?
0.05.
0.05, okay. We could go with 0.5. We could go with 0.5.
I would like to go with 0.05.
Okay, the other thing we're going to need is beta. You choose this. 0.8. The other thing that you're going to need is mu1 and mu2.
But I don't have those yet.
You don't need to, but you don't need to know because you're thinking you have a hypothesized value that says mu1 minus mu2 equals 10. So because we understand statistics, you can say, well, mu1 will be 10, mu2 will be 0. Okay.
So they don't have to be the actual numbers,
No.
it just needs to represent.
If you really understand it,
Yeah.
it doesn't need to be the real numbers.
Like
Okay.
instead of saying 135 and 150, you could just say 0 and 15.
You get the same answer. And I'll show you. We can do this. Okay. What's missing from this is that we now have a delta of 10. That's what you're looking for, right? But if I were to do a study, all right, let's tie this back to the center limit theorem. And I were to do a study, and let's say that I saw a difference between the two means in the group of 10. It doesn't matter what the means are. But let's say I saw a difference of 10. Using words, describe to me what that 10 actually means. How would I interpret that 10? Because we're missing something. It's the thing that everybody always forgets.
The difference between the mean in the treatment group and the mean in the control group is 10.
It's 10, right? But what that 10 really represents is not just the average distance, the average difference of the mean, but it also represents the mean of the means, right? The mean of my average mean differences. So what I need to do is get some idea of how much variability there is in that plus or minus of that 10. So what's missing from my estimates here, and this is the thing that throws everybody, is I need an estimate of what the variance is. And it doesn't matter, essentially, what these are, because these variances pretty much drive everything. All right, now think about this. I'm going to draw something. So we went with 100 and 110 because you wanted a difference of 10. I'm just going to make these numbers up. So I have outcome A and outcome B. What's the difference between the two groups in A?
10.
What's the difference between the outcomes in B? In which study would it be easier to see that 10-point difference? This one or this one? B, right? Why?
Because they don't overlap.
Why don't they overlap so much? What is the explanation for why they don't overlap? There's less variance here. So we need an estimate of the variability of the outcomes in the population. So the more variable something is in the population, the more variance there is, the larger a sample size you're going to need to observe a difference. The less variability, the easier it is to observe the difference. Okay? All right. So that's the other thing that's missing, is the variance. So we had alpha of 0.05, we had beta of 0.2, and I'm just going to write down our delta of 10 because we can put whatever number is we want to get that 10-point difference. The other thing that's important here is, remember there's an assumption that goes along with with correlation, that homoscedasticity assumption. What's homoscedasticity? Homo means the variances are equal, right? So Stata allows you to have different variances for each of the populations, but when we do sample size calculations, we generally tend to assume equal variances. Right? So let's pick a variance. Pick a number, any number. It's not wrong. 5. Okay, so let's plug it in. Let's see what happens. Okay, so I'm going to do a classical test of a hypothesis. I'm going to do a 2-sample, 2-group mean comparison test. Okay, so it's going to break now, correct? Computer's not cooperating here. Here we go. All right. Let's use the commands. So let's plug these things in here, okay? So here I'm going to do samp psi, and I'm just going to go 10, 0. All right, because that's the 10-point difference that you want. I'm going to say the standard deviation is, what's the square root of 5? Let's call it 2.1. 2.1. What else do I need? I need, there's an easier way to do this. Hold on. Here we go, sample size and power determinant. This is what I'm looking for. Okay, so mean 1, 10, mean 2, 0. Standard deviation will be 2.1. 2.1. Okay, I'm going to do this. Now here under my options, I'm going to compute my sample size. And I'm going to set alpha to be 0.5. And you wanted 80% power. You can have a one-sided test or a two-sided test. So this tells me that when I have alpha of 0.05 and 80% power, and a difference between the two groups of 10 and a standard deviation of 2, so a difference of 10 with a standard deviation of 2, that's a difference of, what, like 5 standard deviations differences between the means? You need one person in each group to do this, right? We generally don't see 2. What we generally see, instead of 2, we might see in blood pressure, let's say 20. Right, we're going to see a lot of variability in blood pressure. So when the variance increases, right, under the same conditions, but now we've just increased the variability, we're going to need a whole lot more people to see that same difference, right? So let's hold variance constant. Let's hold variance constant, and let's change the difference. Let's say that the difference between the 2 groups is 1 point. So look at that 1 point difference, because that's a much smaller difference. We're going to need a whole lot more people to see that 1 point difference. To give us 80% probability of seeing that 1 point difference at an O5 level, right? So the reason I'm showing you all of these different scenarios is because when you plan your study, it's a really good idea to come up with several scenarios and say, well, what's the best thing? Well, the best thing is, I'll see this 10-point difference with a standard deviation of 2 in the groups. In this case, I just need to, literally recruit mom and dad, and I'm done, right? Okay, what's the worst case scenario? Well, I'll see a 1 point difference, right? I'll see a 1 point difference, and there's a ton of variability. How many people am I going to need? So it allows you to really think about what could really go on in your study to make an informed decision. The other thing that you can do is we kept power and alpha constant, right? Let's say we were willing to decrease power. We're willing to take a greater chance of not observing the difference, right? So if I change power, say, from 80 to 70%, I'm going to save 2,000 people in my study, right? So you get to see what happens under different sets of assumptions, what could happen. So you get to play the what-if game, right? Which I think is very important, because the thing that nobody ever talks about in science is the cost of doing a study. Given some finite amount of resources, what's the best you could do under some set of assumptions? Given the same set of resources, what would happen if you relaxed or changed your assumptions? Right? And that's a reasonable thing to do. Fair enough? Okay. Now, the other thing that this figuring out, you have some sample size and and figuring out your power after you do your study, never do that. Never, we call that post hoc power. You might as well, just make a goddamn number up, right? Don't do that. What you could do is do a pilot study and look at the variability from your pilot study, and then compute sample size from that. But never do a study and then say, oh, gee, how much power did I have? Well, I didn't reject the null hypothesis because I didn't have enough people. No, that's not how it works. But it doesn't stop people from doing it.
But don't you want to, once you predicted what you thought the means would come out, don't you want to know how it turned out?
No, you know that with your t-test.
Oh, okay.
You know that with your t-test. Now, if you fail miserably, what you could do is you could take fail in the sense that you didn't reject the null. Mm-hmm. You could take that information from your current study and use that to plug in to this for your next study. That's actually how science works. That's called learning. It's funny, but people don't think of it that way. That's science will work. It's got a built-in feedback mechanism. And we often forget that. Pardon?
The built-in feedback mechanism is failure.
Yeah, it is actually. Okay, so we've not yet done ANOVA in regression, but did you do a one-way ANOVA in intro? Yes. Okay. This is how easy it is to do an ANOVA in Stata. So there's actually two commands for doing a one-way ANOVA in Stata. So in an analysis of variance, we don't have predictors, we have factors. A factor would be our predictor, our independent variable. So in ANOVA language, we have our dependent variable and our factor. Our factor is some categorical variable, right? So these two things will do a one-way ANOVA, but the one-way ANOVA command only does a one-way ANOVA, whereas the ANOVA command can do a one-way, a two-way, a three-way, an ANCOVA, lots of other models that we're going to learn, right? If you ever do, I think Judith does something on scales. Do you guys talk about scaling? That's actually my training. I'm a psychometrician. Have you talked about things like interclass correlation coefficients? You can actually, I don't know if you know this, but everything that you probably learn is like a correlation. Maybe you've heard that before, right? Including an interclass correlation coefficient. You can actually do an interclass correlation coefficient using a one-way ANOVA. So in the case of the ANOVA, and the factor would be person. So if you have 1,000 respondents in your study, you have you have all the measurements at time 1, you have all the measurements at time 2. You're going to create a long data set, not a wide data set, but a long data set, and your factor will be the person ID. And then from there, you can compute this command will actually give you the interclass correlation coefficient. Here, you can compute the interclass correlation coefficient from the information, because you have to get what are called expected mean squares and things like that, but this will actually do it for you. So when you use the one-way command, you're assuming that the person is the random factor for the interclass correlation coefficient, if you talked about that stuff. So do you guys know if you can use an ANOVA if you have two groups? Yeah, you can, right? You don't have to have 3 or more, because an ANOVA and a t-test are the same thing when you have 2 groups. Okay, all right. All right. So let's talk about these so-called post-estimation commands, right? So if you recall from our regression tables, before we got down to the parameter estimates, we had things like, we had an F statistic, we had an overall F statistic, we had an R squared, we had an adjusted R squared, we had something called a mean square error. Do you remember that from the regression tables? But on top of the regression table was what I refer to as the ANOVA table, right? Do anybody remember that? Okay. Well, all of these things here are left over when you do an ANOVA, or when you do a lot of estimation commands. There's a lot of things that are left over. Left over in the sense that they're printed on the screen, and there's actually more information left over that's not printed on the screen that you may want to use down the road. So say, for example, I don't know, you're in a class called Advanced Regression, what the hell's the name of 608? Whatever that is. Let's say you're in a class called HPR 608, and you're going to have to learn about things like diagnosing a regression model, starting maybe next week, right? For example, one of the things that we're going to look at when we diagnose regression models, and by the way, ANOVA is simply a special case of a regression model, is we want to look at things like the distribution of the errors, right? Because we made distributional assumptions about the errors, right? We assume that our errors are what? We assume that they're normally and independently distributed with an expected value of 0 and some constant variance, right? We've written this a million times. When you diagnose models, when you do regression, and ANOVA is a case of regression, you can begin to examine these assumptions. So how would I get an error? By definition, an error, statistically, is the difference between the observed and the expected. Right? So if I have an observed and an expected, somehow I need an easy way to get that expected value. In the past, we referred to those expected values as y-hats, right? As y-hats. So by using these post-estimation commands, we can get at our y-hats. We can then subtract our y-hats from our observed values to get our errors. There's also a post-estimation command to get the errors directly. So you don't have to do, y minus this. It'll do it for you directly, and then we can begin to graph the distribution of our errors to see if they're normally distributed, to see if there's constant variance, or do we have heteroscedasticity, and so on and so forth. Okay. The other things that you'll be able to do is, well, there's lots of things you'll be able to do that we're going to learn about. But the idea is to sort of introduce you to the concept. So when you do the ANOVA, if you want to see the byproducts, the leftover stuff, if you type in the command return list, it's going to return a whole bunch of stuff. It'll print out a whole bunch of stuff on the screen. These things that you can use that are left over. The other thing that you can do after you do an ANOVA is if you type in the word estimates, what it'll do is it'll give you your beta coefficients from your regression. Right? It'll give you your parameter estimates from your regression, because I'm telling you, regression and ANOVA are the same thing. Every ANOVA is a regression, but not every regression is an ANOVA. Right? Here are our betas, our parameter estimates. This is how I can get a variance-covariance matrix. I'm just putting it there. Not that we would ever use it in this class, but you could if you wanted. Right? From a variance-covariance matrix, you can compute correlations between your variables, which sort of gets to the idea of, didn't we talk about something called multicollinearity? Right? So we can begin to do that. Okay. So here's I have no financial stake in stat transfer. That's my disclaimer. I have nothing to report, no relationship. But if you can swing this, go for it. This will save you a lot of time, effort, and energy. It takes data from one format and transforms it into another format, which I'm telling you, it will just save you so much time, so much headache. And then, so different. So let's see here. I can think of 1,000 packages. The data can be in ASCII format, Stata, Excel, SAS, SPSS, a DVF, to Stata, or Stata to SAS, and then SAS to FoxPro, and then FoxPro to whatever. Right, whatever. So if you can swing the $59, I think it's a very sound, reasonable investment. And if you get the school to pay for it, all better. It doesn't matter what operating system you have, it'll run on Windows, Linux, Mac. It's really kind of awesome. Okay, there's that. Okay, so now comes the heady stuff. So now comes sort of the nitty-gritty, the hard part. Actually, this really is, I think, the hardest part of doing data analysis. The hardest part of doing data analysis, in my opinion, is reading the goddamn data into the computer. After you get the data into Stata format, then everything's pretty easy. You have all these canned formats and programs that are written for you, but getting it into something that you can work with is a very difficult thing to do. Or not difficult, it just takes most of the time, right? All right. So, we talk about ASCII. ASCII stands for American Standard Codes, blah, I don't know what the fuck it stands for. But anyways, it's a text file. ASCII is text, right? So the reason that we talk about ASCII is that every computer built today, every computer built in the last 30 years can read an ASCII file. Right? Can read an ASCII file. So that being said, it's sort of like the euro of data, right? Or what's that language that they tried to make that? No.
Esperanto.
Esperanto. It's the Esperanto of data formats. Yeah, it's the Esperanto. It's the opposite of the Rosetta Stone. Everything can read it, right? Everything can read it. And if you want to share your data with somebody else, you can export your data from Stata into an ASCII file and send it to them, right? So it really is the Esperanto of data, right? So usually data files, usually, are fairly simple to read in, usually, because what we have we have what are called delimiters. Delimiters are the boundaries that tell the computer program, this is where one field starts and this is where one field ends. So it's the separator, or it delimits one field from another, right? And common delimiters are tabs. This is a pipe symbol, it's not an I. A lot of programs will use commas, so if you save something as a CSV file, that stands for comma separated values. Most programs will be able to read those files in without a hitch. Stata can read those files in very easily. And what it does is it tries to read it in by reading the first, 100 rows or something like that, and then tries to figure out what data type each of the variables are. Remember we talked about data types, strings versus floats and longs and bytes and all that sort of stuff. So it'll try and figure out what those things are for you. It's also very common for ASCII files to have the first row of data to be what we refer to as a header row. The header row contains the variable names. Okay. Now, Stata doesn't allow spaces in their variable names. So if there's a space in a variable name, it'll probably fill it in with an underscore or something like that, right? But reading ASCII files, a comma delimiter or delimited files in Stata is actually very simple to do. There's a command called infile. So it's infile using the variable, the file name. Okay, all right. But sometimes data don't come in so nice. Sometimes you'll get files that are what we call fixed width, right? She didn't like that. I got a hop over there. Fixed width. So what will happen is a fixed width data file will look something like this. Incidentally, your AHRQ data are fixed width files. So the data will look something like this. So it'll look like and you're like, the fuck is that? Sorry. Try not to swear with the thing.
The baby won't.
So the fixed width goes something like this. So you have to create what's called a dictionary. A dictionary tells you how to read this file in. Okay? So what I can do is I can logically take this string, because that's what we can think of it as a string, And we can refer to the positions of these strings. Right? So I have position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So in this case, and let's say that there are more. 12, 13, 14, 15, and I'm going to put some spaces in here. Something like that. Okay? So what we may say here is that in this string, we're going to say that the first position is going to have the sex of the patient. 0 for male, 1 for female. Then we might say fields or columns 2 and 3 contain the age of that respondent. So this is an 11-year-old male. So you have to tell Stata, well, in the first position, it's well, I can store this as a byte because it's only a 0 and 1. This would be probably an int, right? Or actually, it might even be a byte because I think a byte goes up to 127, right? And then 1, 2, 3, 4, 5. I don't know what this is. Let's say that characters 4 through 8 are the person's insurance ID, right? In which case this 0 is meaningful. So I may store this as a string and not a number. Make sense? And then ABC are the person's initials. And then 12 and 13 represent, I don't know, what the hell okay. 13 represents marital status and 13 represents, I don't know, income group or something like that. Well, they're blank. Why are they blank? Because it's an 11-year-old kid, right? So that's meaningful blank data, right? And then I don't know, this is year of birth. I don't know, whatever the hell that is, something like that, right? So you have to tell Stata how to interpret this line of data, how to rip it apart and put it into the variables. And what are the variables? What is the variable name? Do you want to give the variable a label? What kind of data is this? Is it int? Is it just simply a numeric? Is it a string? How big a string is it going to be? So you're basically building a recipe for Stata to be able to read in these files. And this is what you would need to do for your data. Right? Okay. So we call that a dictionary.
So all these files will come with their own dictionary.
Pardon me?
Like all these files should come with their own dictionary.
Not a dictionary, a code book.
Okay.
So a code book is different. A code book should tell you how to create the dictionary.
So then you go back and create the dictionary.
Yes. Yes. Sometimes the vendor or the supplier, if they're Stata friendly, will provide you with the Stata code. But as I said before, many people don't use Stata, so they'll give you a SAS file. They'll give you directions for SAS to read it in. So what we're doing with Kristen's data is I take the data, the ASCII file, the fixed width ASCII file. I take the SAS file that AHRQ provides with it. I run the file through SAS. I then take that SAS file and run it through stat transfer.
So you can't just run the ASCII file?
No. Unfortunately. So this is an example of fixed width format, complete with spaces. Right, so I'm going to take a shot and say that this is probably sitting. Right? So if you look at that, it looks like the matrix, right? All I need to do is animate this, and it looks like the matrix. Right, how do you deal with all that? we have to create a dictionary. And it's 4 o'clock. Okay, so let's stop here. We'll pick up and, okay, so assignment 4 is posted out on Blackboard. Do the best you can. There's part of the assignment is to actually create a dictionary. But don't do that, we're not ready for that yet, okay? Fair enough? But do what you can. And like I said, I'm gonna give you a week to try. And then next Wednesday, I'll post my solution. Kristen and I were talking about this before. There's a million different ways to do the same thing in a computer programming language. So just because I post my solution doesn't mean that it's the only way to do something. So if you and I come up with the same answer, coming at it from a different angle, then guess what? We're both right. Or we're both wrong and happen to get the same wrong answer. Fair enough?
One of the files under assignment 4 is .dat file.
Mm-hmm.
What is that?
Just a text file.
Okay.
Yeah, well, that's the other thing too. Just because the files can come with all kinds of different extensions, all kinds of different names.
Huh?
You ran in cat or dog.
I was just having trouble. Okay.
Well, Windows was because Windows doesn't know how to do it. Yeah. All right. Everyone, okay, so just give it your best shot. I think we meet again in 2 weeks, I think. Okay? We're on spring break now?
3 weeks.
Okay, this is the 3-week break, but in a week, I'll put my solution out there, okay?